Hi, welcome back. In this video, we're going to explore the definition of what it means for a function to be continuous at a point. So here's the definition. It says that the function f of x is continuous at the point x equals a if the limit as x approaches a of f of x is equal to f of a. So let's explore this definition with a specific function. So this is a piecewise function, f of x. It's equal to x squared minus 16 over x plus 4 if x is not equal to negative 4, and it's equal to 0 if x is equal to negative 4. So let's figure out whether f is continuous at x equals negative 4 using the definition. So the definition looks simple, right? It just says the limit has to be equal to the value of the function at that number. Well, three things need to be true in order for that equation to be true. First of all, the limit as x approaches negative 4 of f of x has to exist, so we have to look for that limit. Secondly, the function has to be defined at the number at negative 4, so we have to check that. And then if those two things are true, we have to see if the limit is equal to the value of the function at that number. Okay, so let's do that for this piecewise function. So first of all, we need to find the limit as x approaches negative 4 of f of x. Well, using the first piece, because we got to come from the left and from the right, and for all values less than negative 4 and all values greater than negative 4, we have to use that first definition, the first piece of the definition. So we have to take the limit as x approaches negative 4 of x squared minus 16 over x plus 4. So we know how to do that. We factor the numerator. So this is going to be the limit as x approaches negative 4 of x plus 4 times x minus 4 over x plus 4. Canceling. This is equal to the limit as x approaches negative 4 of x minus 4. Notice I had to write limit in each step. I can't just say that it's equal to x minus 4 because these are not equal as functions. As limits, they are equal, but as functions, they're not. And I have to keep writing lim as x approaches negative 4 in each step. All right, now we can evaluate that limit using direct substitution because now we just have a polynomial x minus 4, and that's defined at negative 4. So now I can plug in negative 4. Negative 4 minus 4 is just negative 8. So the first thing is true. The limit exists. All right, so the second thing is f of negative 4 defined? And according to the definition, f of negative 4 is just 0 by the definition, the piecewise definition. So yes, it's defined. But the third thing, are they equal? So the limit as x approaches negative 4 of f of x is negative 8. And that's not the same as the value of the function at negative 4. The value of the function at negative 4 is 0. So they don't agree. So that part is false. So that means that the function f is not continuous at x equals negative 4. All right. Well, let's see what that looks like graphically. So if we want to graph the piecewise function x squared minus 16 over x plus 4 for x not equal to negative 4 and f of x equals 0 for x equal negative 4, we can rewrite it. The first piece is really just x minus 4 if we factor the numerator and cancel. So it's x minus 4 for all x not equal to negative 4, and it's 0 if x is negative 4. So let's graph that. The first piece is just a line. It's a line with slope 1 and y-intercept negative 4. Y equals x minus 4 is a line with y-intercept negative 4, slope positive 1. But we have to remember we're redefining the value of this function at x equals negative 4. So when x equals negative 4, we have to redefine that point. We have to pull out that point and plop it down on the x-axis because f of negative 4 is 0. So this is what it looks like. It's a line with a hole and then a dot at negative 4, comma 0. All right, so this is a specific type of discontinuity. This one is called a removable discontinuity because it's really easy to remove the problem by just redefining the function. So if we wanted to remove the problem, all we would have to do is redefine the value at x equals negative 4 to be negative 8. And we've removed it. All right, so what's the intuitive definition of continuity? So we know that the definition is that the limit of the function as x approaches a has to be equal to the value of the function at x equals a. So the limit has to exist, the function has to exist at that number, and the two things have to agree. Well, intuitively, we can think of it graphically. We can say that f is continuous at x equals a if we don't have to lift up our pencils when we graph the function y equals f of x. So notice in this picture right above the piecewise function, I did have to lift up my pencil at x equals negative 4. I had to remove a point and then put it down somewhere else. So it was discontinuous at negative 4. All right, so there's 3 different types of discontinuities. So the first type we've already seen is called removable. So here's another example, very similar example. F of x equals x squared minus x minus 2 over x minus 2. Notice that's a line, it's got a hole in it. The hole is at the point 2, 3. And why is that? Well, if we factor the numerator, we get x plus 1 times x minus 2. We can cancel the x minus 2's and we can say this is x plus 1 as long as x is not equal to 2. Remember, when you factor and cancel, you have to remember the information you just got rid of, you have to add it. So we have to say f of x is equal to x plus 1 for all x not equal to 2, or as long as x is not equal to 2. So that's a removable discontinuity because all we need to do to get rid of the problem is just define f of 2 to be 3. And then we just fill in that hole. All right. So the second type of discontinuity is called an infinite discontinuity. And so here's an example. So notice that this function is a piecewise function. F of x is 1 over x squared as long as x is not 0. And then f of x is equal to 1 if x is equal to 0. So this is an infinite discontinuity because we have a vertical asymptote. So even though f of 0 does exist, because it's been defined, f of 0 is 1, and we have a point on the graph, 0, 1. So even though f of 0 exists, the limit as x approaches 0 of f of x doesn't exist. That's infinity, which means it doesn't exist. So that's a discontinuity called an infinite discontinuity, and there's nothing we can do about it. We can't fix it. The third type is called a jump discontinuity, and here's an example. This function is called a step function because it's a bunch of steps. And this particular one is called the greatest integer function. Step functions come up a lot in applications, especially in economics, physics, a lot of places. And this particular one is called the greatest integer function because it's defined for any real number x. F of x is equal to the greatest integer less than or equal to x. So for example, if I wanted to find f of 3/2, the greatest integer less than or equal to 3/2 is 1. So f of 3/2 is 1. But if I wanted to find f of 2, the greatest integer less than or equal to 2 is 2. So f of 2 is 2. So this is called a jump discontinuity because the limits, the one-sided limits, don't agree. At each integer for this particular function, at each integer, the right-hand limit and the left-hand limit don't agree. So for example, the limit as x approaches 2 from the right, so if x is approaching 2 from the right, all the y values are positive 2. But if x is approaching 2 from the left, all the y values are 1. So the right-hand limit and the left-hand limit don't agree. So that's a jump discontinuity. So we've just explored the definition of continuity at a point and looked at a couple of examples graphically. And you're going to have more problems like that in your homework. And I'll see you in the next video.